The topic for today is how to calculate deflections using the method called virtual work. In this video, we'll do a theoretical introduction and some very simple examples. The reason for going over the theory is that this method can seem quite magical, and going over the theory gives you a little bit of confidence that you know that it's founded in very sensible mechanics. Let's get started. Let's remember some background from mechanics and materials. These four equations should look somewhat familiar. The first one is Hooke's law. It relates stress to strain through Young's modulus. The second one has to do with bending stresses in a beam. The third one has to do with stresses in an axially loaded member. And the last one is the definition of moment of inertia. You can consult a mechanics and materials textbook to define all of these terms. We'll also include the work energy principle. In words, this says that the change in external work, so the work done by external forces, is equal to the change in internal strain energy, the energy that's built up in the structure as it deforms elastically. Symbolically, we'll use a capital U for energy, delta for change, and the subscript E or I for external or internal. Let's start looking through these concepts and focus first on external work. I'm showing a simply supported beam. It doesn't have to be simply supported. This applies to any structural configuration. And we'll consider a force that's applied to cause bending stresses. When you apply a force to an elastic member, initially there's nothing applied. As the member deforms, it resists a little bit more, the force gets a little bit bigger. As the member deforms more, the force grows. So we'll indicate the direction of deformation by zeta, and we'll say that the force F is a function of zeta because the force increases as the member deforms. We can also say the same for a force applied in the axial direction. So eventually this force F will reach a maximum value, we'll call that maximum value of P, when the deformation zeta reaches a maximum value. We'll call that maximum value delta. Here we're plotting the force displacement relation. We're plotting F versus zeta. The red line indicates the force gradually increasing as the structure deforms, and eventually it reaches a value P when the deformation is delta. As the structure deforms, we'll look at a small increment of deflection, d zeta, and that will define for us a small increment of external energy, dUE, which is equal to F at that value of zeta times d zeta. I've also indicated here the expression for F of zeta, which you can confirm for yourself. It's the equation for a straight line. So if we're interested now in the total external energy, we would integrate that dUE over the entire deflection. That's the expression that we're showing first. Substitute the equation for F of zeta, perform the integral, evaluate at the endpoints, we get the following expression. Of course, we could have interpreted the integral geometrically. The integral is the area underneath the curve. Well, the height is P, the base is delta, 1/2 because it's a triangle, so it agrees with the geometrical interpretation of the integral. So this then defines for us external work. Let's start looking at internal strain energy. What I've shown here is a small little cube of volume. That small little cube of volume is subjected to a uniaxial stress sigma, which is a function of the strain epsilon. Both bending and axial stresses are uniaxial. Similarly to the load, the stress gradually increases. So when the strain reaches some final value of strain epsilon F, the stress reaches its final value of stress sigma F. The plot looks very similar. We're plotting sigma versus epsilon. We're indicating the final values, sigma F and epsilon F. We're indicating the expression for sigma as a function of epsilon, which you can confirm for yourself. It's the equation of a straight line. And we're indicating a small little increment of internal strain energy as sigma at a given value of epsilon times d epsilon. We'll clarify that this is a lowercase u, indicating that we're still looking at energy per unit volume. We're only looking at that little cube of volume. Strain energy per unit volume we can call the strain energy density. So to calculate the strain energy density, we'll integrate that small differential bit of internal strain energy density, going from 0 to the final strain, substitute the expression for sigma as a function of epsilon, perform the integration, evaluate at the endpoints, and we get that final expression. Once again, we could have evaluated this geometrically. The base is epsilon f, the height is sigma f. We have the factor of 1/2 because it's a triangle, and so we've confirmed our integral by geometric means. So this is our internal strain energy density. It's the internal strain energy in the little cube of material. We're interested in the internal strain energy in the entire member, so now we need to integrate over the whole volume of the member. So the total internal strain energy is indicated with an uppercase U, and it's the integral of the strain energy density over the volume. Substitute in the expression for the strain energy density, and we have the expression that's shown here. Now we'll start evaluating this differently for cases of bending or for cases of axial stress. Before we do that, we'll look at various ways of writing this expression in terms of either sigma or epsilon. So recall Hooke's law, sigma equals E epsilon. And if I make the substitution for sigma directly, I get the first expression. If I solve Hooke's law for epsilon and substitute for epsilon, I get the second expression. The second expression will be a little bit more convenient for our needs today. Let's look at the internal strain energy for axial forces. So I'm showing here an axial rod. It has a cross-sectional stiffness EA. It's a prismatic rod, so the area is consistent throughout the entire length. It's subjected to an axial force N. The member is originally of length L, and it stretches a distance delta sub A under the action of that axial force N. We previously saw that the bending stress is equal to N over A, and we're showing as well the expression for the internal strain energy that we derived on the previous slide. Now it's a matter of just doing the substitutions and working out the math. Start with the expression for internal strain energy, substitute the expression for sigma F, pull everything out of the integral that's constant, and in this case the force is constant. We're assuming that the modulus and the area are constant as well, and so we're left with just the integral over the differential element of volume. Well, the integral over the volume of dV is just the volume. The volume of the rod is its cross-sectional area times its length. We substitute in that result, simplify, and we get that the internal strain energy in a prismatic axially loaded rod is N squared L over 2EA. Let's move on to members in flexure. Here we use the expression for the bending stress. Sigma is equal to minus my over I. And we again write down the expression for the internal strain energy. We'll start by substituting the first equation in the second. That's where the m squared, y squared, and I squared come. The negative sign squared becomes a positive. We'll split up the integral over the volume into two integrals. One over the cross-sectional area, one over the length. When we do that, we recognize that y, which is a coordinate vertically along the cross-section, has to remain in the integral over the cross-section. But the moment, the modulus of elasticity, and the moment of inertia don't vary on the cross-section. So let's think about this. If I draw a moment diagram, there's only one value of moment at any given location in the beam. Similarly, there's only one value of moment of inertia at any given location in the beam. We could have a cross-section with different modulus of elasticity at a single location in the beam. We're assuming that's not the case. So we're able to pull out m, e, and I from the area integral. We recognize the integral of y squared dA as the moment of inertia. I cancels with I squared in the denominator to give us the expression we have here. Now this is as far as we can take it. Every problem is going to have a different moment diagram So m will change for each problem. We have to find m, we have to square it, we have to find the integral, and we have to actually evaluate this separately for each different problem. So now we're able to summarize. We have the external work is 1/2 p delta. We have the internal strain energy for axial forces, or the internal strain energy for bending, given by the expression shown here. We didn't derive this, but we could do a similar calculation as we did for the external work due to a force and calculate that the external work due to a moment is 1/2 m theta, where m is the moment and theta is the rotation through which that moment acts. Let's see how this is applied. We can use this, say, to calculate the deflection at the tip of a beam. So here's a cantilever beam, bending stiffness EI, a load P at the end. It deflects a distance delta at the end. The beam is of length L. The expression for the moment is given at the bottom. This is an expression that you could obtain through beam tables, for instance, or you could have done the moment diagram and written the expression yourself. Start from the basic work energy principle. The external energy is equal to the internal strain energy. The external energy is 1/2 p delta. The internal strain energy is given by the expression on the right-hand side, where I've already pulled out terms that don't change over the length of the member. So if this is a prismatic member, E doesn't change, I doesn't change. And we're just left with the integral of m squared. Plug in the expression for m, square it, integrate it, evaluate it at the endpoint, and we get the expression shown here. We can solve for delta is equal to PL cubed over 3EI. This is kind of neat. We can get an expression for a deflection. This is useful information. We need to design structures for deflections. But there are a number of limitations to this method. We can only calculate deflection at the location of the force. We can only calculate deflection in the direction of the force, and we can only calculate deflection due to a single force. And so there's some very common situations that we simply can't handle with this. What if I have a cantilevered balcony with somebody standing right in the middle and I want to know the deflection at the end? I can't use this method to calculate that. What if I have a simply supported beam with a uniform load and I want to know the rotation at one of the ends because I want to design my connection? This method can't handle that. So this is a pretty severe limitation that we need to overcome. Here's how we overcome it. It's really a quite clever solution. And I'll give you a little caveat that to really prove this properly requires graduate level math. So even the story that I'm giving you here, it's pretty hand-wavy, but you'll get the idea. We're showing a simply supported beam. I'm going to apply to this simply supported beam a virtual force. So this is a made-up force. It's a force that doesn't exist, but I'll assume it's there. If it's there, that force is going to cause certain stresses in the beam, and I'll call those stresses sigma v for virtual stresses. Next, I'll apply the real load. This is the force that's actually applied, that's actually causing the deflections that I'm interested in calculating. And this force also causes some corresponding strains. When I apply the load, the structure deforms, and specifically it deforms a certain amount delta right at the location of the virtual force P sub v. The external work done by the force is the force times the distance. We'll keep in mind that previously there was a 1/2 factor, but here the virtual force was fully applied before the deflection occurred. So we can go back to basic physics. Work done is force times distance. The internal strain energy is similarly sigma times epsilon integrated over the volume. Very similar to what we did before, but we lose the 1/2 factor because the virtual stresses were already fully applied when the strains were developed. Lastly, we use the work energy principle, equate external virtual work and internal virtual strain energy, and through that we find delta. So at this point, I could go through the entire derivation all over. I don't think you want me to do that. This video is already long enough as it is. So let's skip all of that, recognize that the calculations are practically identical to what we did before, and reach this conclusion. The external virtual work is equal to the virtual force times the deflection. Or, if we are applying a moment, it's equal to the virtual moment times the rotation. The internal energies look very similar to what we had previously, with two changes. We lose the 1/2 factor, And instead of having n squared or m squared, we break that up into one component due to the virtual axial load, one component due to the real axial load, or one component due to the virtual bending moment, and one component due to the real bending moment. But what do we do with this? So let's come back down to earth a little bit, and let's see some examples. Before we see some examples, I'm going to tell you some really good news. When we use this method, we don't actually calculate integrals. That's kind of what makes this method useful. If we had to write an expression for moment, multiply it out, do the integral, do all that business, it would be a very long and time-consuming method. We don't do that. We evaluate the integrals with tables. Here's a sample table. A real table is going to be longer. But what these tables always show is the shape of one moment diagram along the left-hand column and the shape of another moment diagram along the top row. And in each of the cells, it's going to tell you what the value of the integral is. Sometimes the expression is a little bit more complicated, but in many cases, the integral is of the form a factor times the height of one of the shapes times the height of the other shape times the base common to both shapes. So for a rectangle times a rectangle, it's 1 times height base. For a rectangle times a triangle, it's 1/2 times height base. For a triangle times a triangle with the heights aligned on the same side, it's 1/3 height base. And for a triangle times a triangle with the heights aligned on opposite sides, it's 1/6 height base. You'll gain more practice using these tables. A few clarifying items. First, you won't always see exactly these same diagrams. I might see a moment diagram that has the tall side on the right side, but instead of sloping up, it's sloping down. What we need to do is we need to look for similar relative arrangements. So am I multiplying a rectangle times a triangle times a triangle with the tall side on the same side, or a triangle times a triangle with the tall side on opposite sides? For instance, the two triangles that are shown with the tall side on the right side are applicable to triangles with the tall side both on the left side, for instance. So we need to look for similar relative arrangements. Secondly, we still need to account for the signs. This tells us the magnitude of the integral, but we need to account for the signs. Well, each of these moment diagrams will have a sign related to it, and we simply realize that if we're multiplying two positives, we get a positive. If we're multiplying a positive and a negative, we get a negative. If we're multiplying two negatives, we get a positive. So, like any work done with tables, it takes a little bit of getting used to how to use the tables, but you'll gain some practice and it'll become second nature fairly quickly. So now let's see an example. We have a cantilever beam, we have a point load at the end, and we're interested in finding the deflection of the tip and the rotation of the tip. The first part of this problem, the deflection, which is what we'll start with, is the same as we did with real work, so we'll be able to compare what we did there. We'll start the problem. The real moment diagram is given here. Now, whoa, this is way too fast. How did you get that? Yeah, we need to be somewhat good at this point at coming up with our moment diagrams. So you need to either be able to do this relatively quickly, getting the reactions at the fixed end, drawing your shear diagram, drawing your moment diagram. Even better, you've memorized the moment diagram for a cantilever. Whichever way you do it, that's the moment diagram due to the real load P at the tip of the beam. Next, we establish our virtual loading and the moment diagram. The rule here for the virtual loading is that I apply a virtual load at the location of and in the direction of desired deflection. So I want to know the deflection at the tip. That deflection is vertical, so I place a vertical load and I place it at the tip. So given that beam loading, I can now come up with the moment diagram. Once again, you need to be able to do this relatively quickly. Now I have my two moment diagrams. I summarize them over here on the left-hand side, and I work on computing my deflection. On the left-hand side is the external work, external virtual work. On the right-hand side is the internal strain energy, and I'm showing picture integrals. So I have the factor of 1 over EI. That first picture is my real moment. That second picture is my virtual moment. I'm going to be using my tables to integrate this. Bring down the term from the left-hand side. The 1 over EI comes out. The integral is computed with the table, a factor of 1/3. Height of one shape is PL. Height of the other shape is PV times L. The base common to both shapes is L. The PV cancels, and I'm left with the answer. Delta is equal to PL cubed over 3EI, which is what we had before, with somewhat less work. You'll notice that the virtual load PV canceled here, and that's critical. Because think about it, we made up a load. We said, let's just assume that there's this load here. We'll call it PV because it's virtual, and we'll do a calculation with it. Well, this calculation is only useful because that virtual load cancels out algebraically. So it doesn't matter what it is. Because it doesn't matter what it is, we can simplify our work even more. We'll just call it 1. Why? Well, because if I multiply anything by 1, I get that same quantity back. And so by calling it 1, I essentially already know that it's going to cancel, and I'm just making my math work out more simply. And so I get these final expressions. The external virtual work is simply the deflection or the rotation that I'm looking for. And the internal virtual work has two components. One that's due to the virtual loading, one that's due to the real loading. The lowercase terms are the axial force or bending moment due to the virtual load. The uppercase terms were previously defined. They're the axial force or the bending moment due to the real load. We can also formalize the steps in the process. Step 1, compute the moment diagram for the real loading. Step 2, apply virtual load at the location of and in the direction of desired displacement. I separate this out as a separate step because it focuses us on the fact that we need to think about exactly where we apply this virtual load given what we want to find. Step 3, compute the virtual moment diagram. Step 4, calculate the deflection, but using tables for the integral. So let's see one last example. We return to the previous example. We wanted to find the deflection and the rotation at the tip. Well, now let's look for the rotation. One nice thing about this method is that the real moment is always going to be the same because it's the same loading, it's the same structure. So the real moment diagram we already calculated. It's given there. We'll apply the virtual loading, that's step 2. I'm interested in the rotation at the tip of the beam. So I'm going to apply a unit moment at the tip of the beam. A rotational force, which we call a moment, at the tip of the beam. Compute the moment diagram. Maybe you can't compute the moment diagram this quickly. Well, if you can't, compute the reactions quickly, calculate that the shear is going to be 0, come up with your moment diagram. So once again, we need to be comfortable with our moment diagrams to be able to use this method well. Place these moment diagrams on the left-hand side here and work on step 4, computing our deflection. To evaluate the integral, we'll use the graphical approach. We have the following terms. The 1 over EI remains where it is. We have the factor of 1/2 for a triangle times a rectangle, PL for the height of the triangle, 1 for the height of the rectangle, and L, which is the common base for both figures. All that we have to do now is to simplify to get that the rotation is PL squared over 2EI. This concludes the rather long introduction to the virtual work method. Thank you for your patience. We'll have some shorter videos after this that just do more examples. The subject isn't that difficult once you become used to it. There are more difficult subjects in structural analysis. So once you become used to it, it'll be fine. So don't be scared away by this long introduction. It's sometimes just nice to know that what we're doing isn't magic, that it's well founded in basic mechanics. Now you can use this method with confidence and start calculating deflections efficiently.